we can use the ideas that we just learned about reciprocal graphs, and now we can graph cosecant, secant, and cotangent. Yeah, and everybody wants to know cotangent for the review. Well, we'll start with cosecant. Again, you start by graphing what's on the bottom, and that I've given to you. I say draw the graph of the function on the bottom. Here's sine already graphed. What did we do first on all of our reciprocal graphs? We started with asymptotes. We have asymptotes wherever there are x-intercepts. So, ooh, look at this. Special asymptote pen. Nice. Yeah. I wanted to design one. You'd have like a ballpoint pen where the ink only worked on half of it, so while you rolled, it would ink and then not ink, then ink, and then not ink, then ink, and then not ink. Maybe. So. But then, I don't know if you would you actually go out to Staples if they had the asymptote pen and buy it, especially for your math class? Yeah, I'm still teaching. Obviously, it's not a good idea. Anyways, we can draw them all in. Adjust them if they don't line up. There we go. And label them. This is x equals 0, x equals pi, x equals 2 pi, and so on. You didn't get one of these? There you go. And now something that hasn't happened in any of our examples so far is we have a function that doesn't go up to infinity or down to infinity. The graph of sine sticks between 1 and -1. So we do not draw an asymptote at y equals 0. This is our first reciprocal graph where we didn't have to draw an asymptote at y equals 0. Next, we do nice points. Well, here we have pi over 2 comma 1. Can you see that that point's going to change, is not going to change, sorry? It's going to stay at pi over 2 comma 1. In fact, every place where sine is equal to 1 is not going to change. And every place where sine is equal to -1 is not going to change. So there's a bunch of nice points. What's another value you know off your unit circle? Yes, you do have to know your unit circle for the final exam. When is sine equal to 1/2? Pi over 6, right? Close enough. You had the pi over right. If you have pi over 6 comma 1/2 on your original function, that means you're going to have pi over 6 comma 2 on your reciprocal graph. In fact, you can just graph up towards the asymptotes or down towards the asymptotes. Probably didn't need to include this many periods of sine, but
so like once we find the graph for one section,
it just is the same every single section. Okay? Now, something that always happens on reciprocal graphs, maximums, local maximums become local minimums. If it's the biggest value, when you do 1 over that, it becomes the smallest value. If it's the smallest value, when you do 1 over that, it becomes the biggest value. Everything goes in opposite directions. Your sine graph is going down, your reciprocal graph is going up. So with that idea, you get to do secant on your own. The cotangent graph gets a little bit messy, especially if you try to do it all on the same graph, which we're going to. We start again, wherever there's x-intercepts, there's asymptotes. Again, I don't know why I had so many. Wow. Okay. Okay. They all lined up. I mean, you could start labeling them x equals 0, x equals pi, x equals 2 pi, x equals negative pi, x equals negative 2 pi, and so on. Okay? Now, nice points. At pi over 4, tan is 1. What's going to happen when the y value is 1? It's going to stay the same. So in fact, you can go across where y is 1, and you could label all of those points where y is 1, because when you do 1 over 1, it stays the same. The same thing happens with another y value, negative 1. So we can go at negative 1 and label all of those points as staying the same. Now, the way that we graph cotangent is we're doing the reciprocal of tan. However, the actual graph of cotangent, you know how cotangent is cos over sine? The actual graph of cotangent is cos over sine and not 1 over tan. Now, cos over sine and 1 over tan are mostly the same. They both are cotangent. There's one small difference. When you talk about 1 over tan, it can never equal 0 because your numerator can never be 0. But when you talk about cos over sine, the numerator can be 0. It can be 0 exactly at the same place where cos is 0. And so wherever you had asymptotes on your original graph are the same places where cos is 0. Does that make sense that your tan graph, if you think about tan as sine over cos, all the asymptotes on tan are where cos is equal to 0 because you're not allowed to divide by 0. But now, if you think about cotangent as cos over sine, everywhere where there's an asymptote is actually where cos is 0, and so these are additional points on your cotangent graph. Now with our red asymptotes, our green points, we are going to get a shape similar to our tan graph for our cotangent graph. Graph it towards the asymptotes. It's just the opposite, which kind of makes sense because that sort of seems to be how reciprocal graphs had worked. Oh, don't want to get an E9 error. Put those arrowheads on. And that's the graph of cotangent. Question? Yes, because, that's a good question. He said, if the tan graph goes up forever, why isn't there an asymptote at y equals 0? Because, again, we're graphing cotangent as cos over sine as opposed to 1 over tan. We're using 1 over tan for the basic idea, but because we're actually graphing cos over sine, we don't have an asymptote there because we actually have values of 0 at those places. So the tan graph, technically, the 1 over tan graph would look exactly the same with holes there. And the cotangent graph has those holes filled in. Ugh. So there's your cotangent graph. And now you can do that question on your first review.